No, good. Yeah.
So it's a great pleasure to introduce another homomorphic mirror symmetry legend and a friend of mine for many, many years, Seidel, who is going to tell us about quantum Steenrod operations and homomorphisms. Paul?
Yep, thank you very much. Okay, so, right. It's small, okay. 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 So first I should say, a few words about Kenji. Kenji is awesome. Okay. So now this is a pretty unexciting series of talks whose aim it is to give you a break between Kontsevich and Pardon. So in part I just decided, because there are many people here who know stuff better than I do, to just see whether I can use this to have somebody explain my own ideas to me. Okay. And so what I would very much need, if there's somebody here who knows, can compute quantum periods of Fano threefolds, please come forward at the end. And I also have some issues in topology about Steenrod power operations. So if you'd like to talk about this. Okay. That would also be very highly appreciated. So, so what do I actually have? Okay. So the motivation is as follows. Okay. So if I have, suppose I have a symplectic manifold, and let me suppose for simplicity that it's Fano, or as they call it in symplectic geometry, monotone. Okay. So then we have the Fukaya category, and one thing that this monotonicity makes it easy is actually defined over the integers, right? And then so this is something that well, we can partially compute in many cases, like the superpotentials associated to Lagrangian torides can be computed over the integers. Okay, but to completely determine this tends to be, it's not entirely straightforward. It's been done in some cases, but even for x equals CP1, there's some, non-trivial arithmetic aspects that I learned from Yankee. What I would like to look at is the d-pic of f of x. So the group of symmetries, the derived Picard group. I put group in quotes because it's some object of derived geometry, so it's not really an algebraic group. But again, it's defined to the extent you could say it, it's defined over Z. This is, even if you know the category, this is kind of complicated to figure out. So I would like to restrict to the component containing the identity. And in fact, I would like to restrict even more to the formal completion around the identity. Okay. So this is a formal group. This is a formal group over Z. Okay. And so if you assume, for instance, that maybe some part of the Fukaya category is the derived category of is mirror to some elliptic curve that's defined over Z, then here you get the derived automorphism group of the elliptic curve, which is 2 copies It's the elliptic curve cross peak 0, and here you would get the associated formal group over Z, which contains a certain amount of arithmetic information. Okay? Well, this is all very nice. The problem is, you know, if you already know this, why would I bother to, you know, yes? Actually, this is one of the interesting things. Okay? So yes. So it's one of the interesting points. I'll get to that maybe in lecture 2. Okay. So well, in short, yes. So yeah. So the idea is that maybe this one here we can actually you know, understand more simply, and it's more amenable to computation because it takes place in a formal neighborhood of the identity endomorphism of the category, and hence it's amenable to computation in the closed string sector. But the proof of the pudding is whether you can actually make this work and give explicit computations. Okay? So I'm sort of in the middle of thinking about it, and no part of it I really fully understand. So if I say theorem, it means conjecture. If I ever write conjecture, it means, oh my God. Okay? So with that in mind, let's do some, let me introduce some, you know, so sort of preliminary homological algebra exercise. Okay, this is stuff that I will not be using again, but you know, obviously in a purely algebraic setting, you can see the things much better, much more easily. So let's start with A, which is a sort of A infinity ring. Okay, so it's a graded free abelian group. So working over Z with an A infinity structure. That's, you know, it's one, the differential, the product, higher order operations, and so on. Okay? And then I want to say that C is the Hochschild complex. Okay, so the cohomology of C is the Hochschild cohomology of A. Okay, so C is the product some shifted version of A. Okay, so I would like to. So this carries, you know, the Hochschild cohomology carries a number of very well-known structures, you know, product and the bracket and so on. But here I'm interested in reduction to with Z mod P on the finite field coefficients. Okay, so I would like to remind you, important fact in algebraic geometry. So in characteristic P, if D is a derivation of an algebra, then so is D mod P, by which I mean the pth iterative. Okay? So the pth power of a derivation is again a derivation. Okay? Okay, let's say A. Okay. So note that, why am I talking about this? Note that, you know, the first Hochschild cohomology of A is derivations mod inner derivations. Okay? So this is, you take a class in HH1 and there's a pth power, and it actually, you know, it descends to the quotient by inner derivations. Okay? So there is a pth power operation. Okay? So now I take the Hochschild cohomology of, well, let's say in degree L of A with coefficients in Fp. I think this is kind of self-explanatory. I tensor everything, just like cohomology of a space with coefficients in Hp. And I map it to P, so P times L plus 1 minus P, AFP. Okay, let's call this H psi to distinguish it from all the other big psis which will appear later on. So this is so for L, this is defined for L odd, at least, you know, if P is 2, or for all L. P is equals to 2. Okay. This is, of course, not a new observation from purely, you know, algebraic point of view. Well, there's a, whoops, it's spelled out in a nice paper by Turchi. It's not me, okay. But it actually, you know, you can sort of read it off from the structures that McClure and Smith introduced in their proof of the Delian conjecture, which their proof works, the Z. So how does this work here? And so this generalizes this observation here. If you start with HH1, right, then you get HHP plus 1 minus P, you end back in HH1. Okay. So how does this work? Okay. So the underlying chain map okay. The underlying chain map. Okay. So this is a map from C to C. Okay. And it takes, you take a Hochschild co-cycle C, okay, and you map it to the following thing. So there's a sum over rooted trees with P vertices, okay, and so this a tree, okay. So let's say this could be a tree, okay. And then you write this one here, so you put at every vertex of the tree, you put a copy of your Hochschild cochain, and then you put, you know, so okay, there you go, okay. Okay, so this gives you a multilinear operation, right? So you take here the inputs, this is a tree, so it goes, you know, rooted tree means there's a distinguished end, which is the root. So you put elements of your algebra here at all the incoming things, then there's this propagator where you just apply C and you repeat. Okay?
So the chain map, though.
Excuse me?
It's not a chain map.
It is not a chain, well, it's a non-linear chain map, right? It's not additive. Okay?
Yeah, well, that's kind of chain map.
Chain-
For sure.
Chain level. Okay. So yeah, so this is not, of course, additive because it's a p power map. So when you prove that this is, well, okay, let's just a second. I haven't quite finished the description here, okay? Because there's a multiplicity here for each tree, and the multiplicity is the number of causal orderings of vertices. I just made up this language, okay? So what does it mean is you order the vertices in such a way that the order increases as you go towards the root. So this guy here, of course, it has 1, but this one here has 2, okay? Because this is vertex number, has to be vertex number 3, and this is vertex number 1 and 2, but you could also swap them. So there are 2 possible causal orderings, okay? So,
are you writing like the total power operation, or?
This is the p power operation. They're exactly p vertices, okay? And that's the only thing that actually. So okay, right. So so just in case. Okay. So example. So if you, in the simplest case, p equals 2, you've probably all seen this before, right? So you only have one tree here, which looks like this, okay? So this is the so-called circle product, okay? So this is the, well, circle product actually precisely C circle C, okay? So if you do this normally, this is the operation, the sort of bilinear operation on Hochschild cochains, which proves the homotopy commutativity of the ordinary product, and which, if you antisymmetrize it, gives you the Lie bracket. So this is, half of the Lie bracket, right? And in fact, more generally speaking, it is true that the bracket, together with this operation, makes Hochschild cohomology into a restricted Lie algebra. Okay? So that because it's non-additive, the proof that this actually makes sense involves two things. One, if it's a co-cycle, you have to produce a co-cycle, and if two co-cycles are homologous, then the outcome is homologous, right? But let me look at the previous thing. So C is a Hochschild co-cycle. Okay, so this means what in this graphical notation? If you take, oops. So the Hochschild differential works like this up to signs. You put in the A infinity structure of the algebra here, and then, okay, and this is equal to 0. Okay, so then. Okay, so apply the Hochschild differential to our operation. Okay. So we look at this tree here, and so we know that each C is a Hochschild cocycle. Okay. So you can express it if it's 0 by putting in a mu before that or a mu after that, okay? And so if you have an expression here, sorry, this is somewhat schematic, okay? This is a mu for the operation. So if you use the fact that this is 0 and you apply it to all vertices, you will get these kinds of things occurring twice. Once because this is C and mu coming from the fact that here you had a cocycle, and one mu and C because here you had a cocycle. Okay? So these ones here cancel. Okay? So you get, because each edge occurs twice, then you get the desired thing. Okay, so you have these trees here. Okay, so the sum of the trees, where you have the mu at the output, okay, okay, then you have the trees, where you have a mu here at the input, okay. So you could say, well, this is exactly proof that it's a Hochschild cocycle. Note that I haven't actually used the fact that I'm in characteristic. I'm using coefficients mod p. Right? So the problem, okay, I'm going to throw everything that doesn't write on the floor, and then by process of elimination, the ones that work will be left. Okay, so the problem is this one here, okay, which will occur when you do this kind of argument, where you have an infinity structure at the bottom, and you have at least 2 branches with elements of C on it, okay? But now you have to think about, again, these things come with, but this appears, is counted. Okay? Remember, the vertices that carry C's still have causal orderings, right? And because this part is divided on 2 or more branches, what the causal ordering, you first determine the subsets of orderings that occur in each, and those subsets can be freely permuted by the action of, say, the cyclic permutation Z mod P, and therefore they always occur with a multiplicity that's congruent to 0 mod P. Okay? So this is the proof that it works. Okay. Happiness? Good.
Wait,
Yes?
Sorry, I'm confused. How do P... Okay, so P... 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 P...
Why is it the same P that comes up in... Can you say again the last sentence?
Take rooted trees with P vertices. Take the sum
Yeah,
of all
so
the
you have rooted tree with P vertices, right? So the multiplicities that appear here, right, they are something that's internal to each subtree here, times a multifactorial, P choose, multi-choose, P choose I1, I2, and so on. Non-trivial, and those ones are always multiples of P.
Okay.
Okay, sorry about this. So this is this operation here. Well, I would like to explain this as a piece of something slightly more general, right? So let's return to a general A infinity ring A. Okay, and so given such a ring, so we can consider solutions to the Maurer-Cartan equation. Okay, so they are, okay, 1 second, I will correct this in just a second. So the Maurer-Cartan equation is just this equation here. Okay, so now because this is an infinite sum, we need to do something here, okay? To make the sum truncate, okay, so where n is, let's say, a non-unital adic ring. Okay? So it's a commutative ring. With n is isomorphic to the inverse limit of n, the n to the n. Okay. E.g., think, z. Well, this isn't quite true if you put a parameter t, because that's the problem. Okay? So this is going to be a deformation parameter, and you can think of this so that you can look at solutions of the Maurer-Cartan equation, and two solutions are equivalent. So A1, A2 are equivalent if there is an H in A node such that A2 minus A1 is equal to the sum A2 and so on and so on. So there's a bunch of A2s, then an H, then a bunch of A1s.
Oh, why did you put
Yes.
the T at the front of your...
Excuse me?
Why did you put the T at the front of the power series?
Oh, it's a non-unital one, right?
Oh, okay.
I mean, I want really every element to be sort of topologically nilpotent. Okay? Well, you could adjoin the unit by joining a copy of C, but I'm going to use the maximal ideal anyway, so why don't you just use the maximal ideal? Okay? So this is, and so then there's, so we define MC of A with coefficients in N to be the set of equivalence classes. Okay, this is a standard way of setting up a sort of deformation problem as a functor from some kind of coefficient rings, in this case these adic rings, to sets. Okay, it's a functorial, obviously.
Get the denominator somewhere in the formula.
Excuse me?
Don't get the denominator somewhere when you divide roots and exponents.
No, in this case, actually, I don't. So so the point is, yes. So you could think of it as a problem that takes place in the L-infinity algebra. That's obtained by anti-symmetrizing this, but I think you're multiplying and then dividing and so on. So there are no, this problem is actually, it's not, I don't want to use DGL, differential gradient algebra formula for information theory, because it's characteristic zero thing. Okay? So this is it. So just as an example, you can think of the case where n is just an abelian group with the product being 0, right? So n squared is 0. In that case, anything involving a product is 0, so this equation just says that it's a cocycle, and this equation just says that the difference between those two cocycles is mu1 of h. Okay? So if n, so example, okay. So if n squared is equals to 0, then this Marocatan of a n is just h1 of a with coefficients in the linear group n. Okay? So if you like, you can think of the more complicated MC, which are just sets, as nonlinear analogues of cohomology. Okay? So the question is, okay, this is some kind of deformation theory. The deformation theory of what exactly, right? Well, it's not the deformation theory of A as an A infinity algebra, right? Because there's not enough structure here. What it is you can think of it as follows. Inside the category of modules over A, there is the free module A, and this is the deformation theory of the free module, or the deformation theory as a curved twisted complex. It's, in symplectic geometry, it's these things which we call, trying to find a bounding co-cycle, bounding co-chain, Okay. So, so this is not. Excuse me?
Just a module, not a bimodule.
It's a module, yeah. So, but now I'm going to, okay. So I don't want to apply it to this one here, but so the Hochschild complex C also has an A infinity structure. Okay? So mu1 C is the Hochschild differential. Which is actually a bit exceptional, and the next term, so this I already wrote this down, so I'm not going to write this down anymore. Okay, so the next term here is mu C2. So this involves you use two Hochschild cochains, okay? And what this looks like is, so you take the multiplication of A, okay, so the A infinity multiplication, and then you stick in C2, and C1 here. Okay? And all the higher order A infinity structures look like this. Okay? So now, what I want to look at the Marocatan equation in C. Okay? So this gives you MC of C in the Hochschild complex, comma n. Okay? This is, again, it's not the deformation of the A infinity structure on A, because I didn't use the bracket on the Hochschild complex, I'm using the product. So this is now the deformation, if you like, of the diagonal bimodule over C as a bimodule, right? And as such, obviously, it has, as is very familiar, too many people here thought about the Berlin conjecture, it has additional structure. So let's say it like this. So let me call the Marocatan element, so gamma in C is a Marocatan element if and only if, well, let's say it like this. We say phi d is so let's say gamma d for d. So these are the multilinear parts, 1, and then on the linear part I want to add the identity. Okay, so then this thing here is an A infinity automorphism of possibly curved, right? Of A. So I make it the unit, right? I mean, what does it mean here? The identity, because I'm with coefficients in n, right? N doesn't have a unit, so I have a unit here. Okay. Which reduces the identity to the identity over Z1. Okay? So in other words, these are deformations of the identity functor, formal deformations of the identity functor, inside the automorphism group of A. Okay? Possibly with curved A infinity automorphisms, because the Hochschild cochains can have a constant term. So this is not this is not a hard theorem in any sense. Okay? So what happens is when you look at the Maurer-Cattan equation, it has maybe I should say that. Okay. So, all right. Let me try to. Am I doing things okay? I'm temporarily confused. Sorry. Let me. Okay. Let me go on before I totally confuse myself. Give me a sec. Yes, that's okay. So when you look at the higher order multiplications just have a bunch of copies of C, right? So if you add up the Maurer-Cattan equation, what you see is mu, where you can insert as many C's as you want here. And then the other one where you have a C and you insert a mu somewhere, which comes from the differential, and that's just the definition of an A infinity homomorphism. Okay, so automorphism just means it's just a it's a homomorphism that reduces to the identity. They're automatically invertible. Okay, so now obviously so A infinity homomorphisms can be composed. So this leads to a composition law for these elements gamma, to a composition law for Maurer-Cattan solutions. So these elements here in the Hochschild complex. Okay, which I will write down for you explicitly, okay, which is just the composition of A infinity homomorphisms, okay. So this is, so first of all, it's gamma 2 plus the sum, okay, let me draw it the other term, so gamma 2. So this one here is again in sort of tree notation, okay. You can put in as many gamma 2s here as you want. Okay? So by the way, so here is so any number greater than or equal to 0 of gamma 2s. So in particular, there could be no gamma 2 at all. So there's, if you wonder the asymmetry, there's gamma 1 plus gamma 2 plus something. Okay? So in particular, if you assume that n squared is 0, then the Maurer-Cattan elements are just Hochschild cohomology classes, and the composition is just addition of such classes. Okay? So the consequence is that this one here, Maurer-Cattan elements of C, is a, well, formal group, meaning a functor from adic rings N and two groups. Okay. Now I do notice that usually when you say a formal group, there's you can define a formal group to be something like this as a functor, but then usually there's a whole bunch of additional axioms that you impose, which then lead to some kind of representability. I think it's clear to everybody here that what I'm doing here is some kind of truncation of an object from derived geometry. You can't really expect it to satisfy those properties, because then it would be representable by something that's not a derived object, and that's definitely not true. Okay, but so I just call it a formal group in quotation marks, and there were already quotation marks at the beginning when I used these things. Okay, so remarks. So MC is not commutative in general. right? You take your favorite object from algebraic geometry and you model its category of coherent sheaves, and then you get a piece of the formal completion of the automorphism group, and there's no reason why the automorphism group should be commutative in general. Okay? So the other remark is, okay, now that the other, okay, so. Okay, so the deformation theory is unobstructed in positive characteristics. In zero is in characteristic zero, but not in characteristic greater than zero. So what do I mean by this? So if you have, let's say, a Maurer-Cattan solution of this one here over Fp, so this is just a Hochschild cohomology class in Fp, and you would like to extend it to second order, okay? Let's say it's, you introduce this parameter t, and then you divide out not by t squared, which would be this, by t cubed. So this one here is not surjective. Okay. So certainly in characteristic zero, there's, you could prove, so if you put here q instead of fp, this is always onto, which you can prove by a sort of simple argument using the group structure, which has a name. What's it called?
It's like saying that the group scheme cannot be reported.
That's right. It's just saying that group scheme cannot be reported. But it follows from the group structure. But if you look carefully at the argument, you're actually dividing by 2. So well, let's say here, because I'm doing first order, let's say that I'm going to do this, because property P is F2 and F2. Okay. So how do you see this? Well, so example is to take a central element of the first cohomology with coefficients in F2 whose square is non-zero. So a central element, let's say you just take an algebra or something, well, you're assuming that, so the central elements are sort of constant components of Hochschild cohomology classes. Let's assume that this can be extended to a Hochschild cohomology class, okay? And then if you see what it means to have a second order deformation, that implies that the square is 0, which of course is not generally the case, okay? You can say, well, but Paul doesn't understand deformation theory in characteristic P. Instead of extending it from F2, I want to extend it to F4. Okay, but that you also can't do, and the obstruction is much simpler, which is it's the Box-Dean of the central element. Okay.
But you need not F4, but Z-mod 4.
Say again?
Not F4, but not
Z-mod 4. Did I say F4? Oh my God. Z-mod 4. Z-mod 4. Okay. Z-mod 4. Okay. So now I have to bring together these two pieces of the talk. Okay. So the way that you look at formal groups, often, to get some explicit information about them, is that you just consider, instead of the multiplication, you just consider maps that take an element to its mth power. So actually m-fold multiplication in the formal group. Okay? And so it's a fact. So I want to take so there's a Maurer-Cattan of C, okay? Coefficients in something, Maurer-Cattan C, coefficient in something. And here I want to take the pth power map, okay, of the formal group. So it's like p-fold multiplication applied to some element, and I'm terribly sorry this is, okay, so I want to take this one here, and I would like to divide by, I can do it over anything, right, by t to the power p plus 1. Turn out in just a second, yeah? So the highest non-trivial power of t is t to the p. And here I do the same thing, t f p t over t to the p plus 1. Okay? All right? I mean, the p power map exists over any coefficient field, but here I want to project to where I divide out by t squared. Okay, so this one here is just h1 of my algebra with coefficients in fp. Okay? And here I want to inject, Mauro-Cattan, I want to inject Mauro-Cattan operations which have a t to the p coefficient, fpt, over t to the p plus 1. Okay? Here again, there's a ring where the square is obviously 0, so this is also hh1a fp. And this obviously injects into here. Those are the Mauro-Cattan solutions that have the lowest power as t to the p. So again, it's a linear problem. Okay? And here you have this operation here, hh theta. Let's put it in a prime. Okay? So in other words, you take the p power map, and its first non-trivial term is given by this operation here, which hopefully is easier to compute. Okay? So why are you interested in this? Well, let's think about, this is the kind of simplest case where formal groups can occur, let's say, in the arithmetic of elliptic curves. Okay? So your first question about an elliptic curve is what is its height over any p of the formal group, and the simplest question about the height is the height 1 or not? Well, if not, it's actually 2 in this particular case, but and so this is exactly the information that you would need. The leading order term of the p power map, the thing that goes from t to the p, that if that is, well, in an elliptic curve, this would be one-dimensional in the classical arithmetic framework. If this is non-zero, then it has height 1. Okay? So, okay, I am not claiming that this is in any way original, by the way, okay? In the future, when the archaeologists, excavate the ruined foundations of Lomonosov University, they will find it written on a clay tablet somewhere from around 3000 BC. So what is the proof? Okay. So so let's look at the p power map. Okay. So you apply it to some Mauro-Cattan solution C, and it's the sum. Okay, again, you look at the composition law here. So you take all these to be equal. So it's a Mauro-Cattan equation gamma, and you stack p. You do this p fold with always the same thing. Okay. So let me temporarily. Okay. So there's of course, there's also the terms where you don't have. I mean, this one here, they're not all trees with 2 layers, right? There's the tree gamma 2 and just the tree gamma 1. Okay. So you have the sort of trees. Okay, at the moment, and let's say p composition. So gamma 1 compose gamma p, okay? And so here you have, let's say, the gamma p, and here you have some gamma I, and so on, and so the order is increasing, right? So you sum over rooted trees whose vertices are labeled by 1p causally, which means again okay? But you can repeat, so as you go down towards the root, it increases because you compose them, right? And a secret now, really the case that's interesting for us is of course when these are all gamma. Okay? Okay. So now, so in principle there is not, because of the causal ordering, you can't have more than p vertices stacked on top of each other, but you can have an arbitrary number of vertices. Okay? So in our setup, trees with more than p vertices contribute trivially. Okay?
Because that's fine.
Because of this coefficient thing. So every input comes with the power of t. If you have put more than p of them together, you get t to the p plus 1, and so that is trivial. Okay? So now let's look at the trees that have exactly p vertices. Okay? Well, let me suppose, for instance, so these p vertices come with labels 1 to p, but the labels don't a priori have to be distinct. Okay? So suppose that you're not using all the labels. Okay? Then your process takes place in 2 steps. First, you have to determine the non-trivial subset of 1p, which you will use for labeling, and then you have to label them. But of course, the choice of that subset is congruent to 0 mod p. Okay? So trees which do not use all labels, contribute something that's congruent 0 mod p. And this is very important because in particular, it leads to the cancellation of everything that has power less than t to the p, which is not obvious, which is something that I claimed here. And so what you're left is with trees which have exactly p vertices and which have distinct labelings, which is exactly the causal ordering that I was talking about before. Okay? So it's essentially a exercise. Happiness? Okay. So now, this is sort of the elementary algebra. So I would like to obviously do this geometrically and, you know, sort of the proof of the Delian conjecture tells us how we should go about thinking about this. And so there are certain amounts of modular spaces. So I would like to remind you, so let me not talk about symplectic manifolds yet. I will just talk formally in terms of sort of operands. Okay? And so first there are the Stashev spaces. Okay? So let's say S, D. Okay, so the Stashev polyhedra, associahedra, so are compactifications of, well, you take points that are ordered, D points, on the real line, and you divide by translation. So this is translation and expansion. Okay, translation, this is translation, sorry, and yes, you can scale. And just to make this clear, so so this is the interior of the space of SD, and so the degenerations look like. Okay, so you have these, and then you have a sort of screen where you look in microscopically and you figure out which points came together here. Okay. And in principle they can be stacked. So this means that, you know, this was a limit in which these 2 points came together, so they're 1, 2, 3, 4, 5, 6, 7, 8. These 2 points came together, 7 and 8. 1, 2, and 3 came together, and this limiting tells you what their relative speed were at which they collided. Here 4, 5, and 6 came together, but 4 and 5 came together much faster than 6 did, and so you have 3 screens. Okay? And so, you know, so if you have, suppose that I have a chain complex with operations that are given. So this is an operand. You can compose these screen things. So you have, I'm sorry, you know, I always have some issues about grading. So with chain maps here, okay. Sorry, I reversed the grading here because I'm thinking of these chain complexes as cohomologically graded. But never mind. So if you have something which is an algebra over this is an unsymmetric operand, then we get the structure of an A-infinity algebra. How do we get the structure of an A-infinity algebra? Well, by specializing it specializing to a suitable fundamental chain. Okay, so SD, it's a chain of degree d minus 2, the top degree of SD. Okay? And these chains are constructed iteratively. This is a manifold with corners, okay? And the boundaries are products because the codimension 1 boundary faces are ones where you have 2 screens, and so I plus j equals d plus 2 Si cross Sj. Okay. This is the whatever outer product on chains. Okay, so if you let those act, then from these relations you get the A-infinity associated relations, which everybody here, I suppose, knows. Okay. So the two-dimensional counterpart of these Stasher spaces are the sort of Fulton-McPherson spaces. Okay, let's call them Fulton-McPherson D. Okay, which are compactifications of so now points in the plane which are distinct, divided by translation, and again I want to use radial rescaling, I don't want to use rotation, okay? So translation and scaling. So again, the degenerations are like this. So you have you have some places may have collided, and then you have screens here, which describe how things collided. Each screen contains at least 2 points, right? Otherwise, the space is not actually defined. So. So again, we can think of, think of a chain complex that has a structure. This form an operate, this is like a symmetric operate. Well, one difference between this case and that case, Fulton-McPherson spaces, is the Stasher spaces are contractible, right? So there's nothing there essentially other than the top dimensional chain. You don't actually lose anything. But the Fulton-McPherson spaces have very rich topology. So the simplest one would be FMD is S1, right? So you have these 2 points. You can translate them and you can scale them, but you can't rotate them. So the angle is invariant, and so this is actually S1. So FM2. Excuse me? FM2. FM2, excuse me. There you go. Okay. So of course they are, this is equivalent as an opera to the classical little disc or little squares opera in algebraic topology. So so note that. So you can actually map the Stasher spaces here by just, you say you have these points here and you put them all on a line, okay? And this is sort of compatibly with the operant structure. Okay? And okay, so in particular, so if C is an algebra over these chain groups of FMD, it is also an infinity algebra just by using these particular cycles here, right? And so that's what I've done before is an example of this. So the Hochschild chain complex is actually an algebra with a chain level Fulton-McPherson operand. And at first I said, well, it's an infinity algebra, so we consider Marok-Katan solution, but then there was extra structure. Okay? And so the next fact is, so if C is an algebra over chain of chains of
It's almost invisible.
Excuse me?
It's almost invisible.
Yeah, God. It's because of the yeah. If C, this is a chain concept. Was that?
Yes, such a big difference, yes.
Okay, this is the last case. So if C is an algebra over the chains on the Fulton-McPherson operator, then MC, okay, so MCC, so the Maurer-Cartan elements as a functor has the structure of a formal group. Okay, in the same sense as before, but now defined geometrically. So that is what I will do next time. So it's sort of a geometric version of the previous argument, and it brings in some very nice additional moduli spaces, the bi-associahedra of Mao, Wehrheim, Woodward, and Botman, which define the formal group structure. And then we can ask ourselves, since I have this formal group structure, you know, what expression do I have for the Pith power maps in the same sense as before? And it turns out, well, the solution to that goes way back before the Deligne conjecture and so on, and involves Fred Cohen's thesis work on operations on double loop spaces, which I will explain next time.
Questions?
Okay, now I don't remember if you know how to compute quantum periods.
Okay, so let's take 4 again. So let me make a couple